Okay, guys, let's go ahead and continue the notes from where we left off. So we are taking a look at our new target, EI.2 notes. It's an addition to EI.2 notes, linear and absolute value inequalities. It is an addition to EI.1 notes that were about linear and absolute value equations. So the things that we learned in the first target, we're going to continue to use those, but we're going to develop them a little bit further. Let's go ahead and let's go look at some examples of how we can represent inequality. So problem number one says, for each of the following, model the given phrase using the correct inequality symbol, the symbol that we learned back in Algebra 1, then state the result in interval notation and graphically when possible. We're actually going to do graphically first and use that to help us to go into interval notation. So let's jump right into problem 1a. It says x is greater than k. Remember that we had these inequality symbols that look kind of like a part of a triangle here. Those symbols we are going to use to help us to represent values in relation to one another. So it says x is greater than k. So how we would write x is greater than k is x, and that symbol right there means is greater than k. So the opening of the symbol is to the value that has great, or the expression that has greater value, in this case x. So this would be the inequality. We also want to be able to graph that. So when we graph that, all of these are going to be represented on a number line. So the number line here, we can draw out a number line and it's going to go to the left forever. It's going to go to the right forever. We want to relate or show the relation of x to k. So k is somewhere on that number line. We don't know exactly where, but it's somewhere on that number line. What we then can do from here is identify that x is greater than k by how we fill in the number line. So k is at this location on the number line. When the graph is not equal to k, we're going to leave that with an open circle. That open circle shows us that we are getting as close to k as possible, but we're not actually going to be equal there at k. If it is greater, our graph is going to continue to the right. It's going to go to the right. Remember, as we increase on the number line, we're moving left to right. So we want to shade everything to the right. So this graph here shows the representation of a value being greater than k. Now, if we want to put that in interval notation, what we would do here is we're going to have a new symbol. We're going to write x, and this symbol means exists within. So x exists within the interval, and we always start as far as we can to the left. So the furthest left right here on this number line is right there, right next to k. So we're going to start this interval with k. We're going to put a parenthesis around k to show that we are not equal at k. So the interval starts at k, but it's not actually equal at k. Then this interval continues to the right forever. So it's going to continue to the right for on and on. And so it's eventually going to go to infinity, or in the direction of infinity. Infinity always gets a parenthesis because we cannot actually reach infinity. So this would be the representation x is greater than k, a graphical depiction of that, and then an interval that shows us that x exists from k to infinity. In B, we switch up the value. So x now is less than or equal to k. So if we had x was greater than k in the first screen, now we're going to have that x is less than k. So we're going to switch the direction there of that inequality statement. But it's also equal to, it's less than or equal, so we want to make sure we put a little bar underneath that inequality. That little bar underneath the inequality represents being equal at k. So as we graph this again, we want to start a number line. We start with k on that number line. Now this time, because we are equal to k, we're going to fill in the circle. It's going to be a closed circle over the top of the k, or a dot. If it's less than k, that means it goes to the right. So if you think about a number line, the negative numbers go in the direction, if it's less than k, it goes to the left. The negative numbers go to the left. So this shaded region to the left represents that we are including k, but also everything left of k. Our interval notation here would be the leftmost value. So this goes left forever. So leftmost would be negative infinity. So we'd go from negative infinity all the way to k, this time including k. So there's a bracket around k. That means that we are equal at k. That's part of the interval. Now, negative and positive infinity always have a parenthesis because we can never reach that value. Let's take a look at C. C starts to throw in what we call a compound inequality, which we will go a little bit further in the next video. So in C, it says x is less than b, but greater than a. This word but can also be written as the word and. So x is less than b. If I represent this here, this would show us that x is less than b. So the equality symbol is opening towards b. It's also greater than a. So I'm going to go ahead and combine these two and have an equality symbol opening the x, saying that x is greater than a on the other side. So if I read this in one string here, the way that it's written, it would say a is less than x, that is less than b. That's okay. It still means the same thing as x is less than b and or but greater than a. Now in this case on the number line, we're going to have two values to represent. A is less than b here. We can deduce that by the wording. So a is going to be to the left of b. We know that we're not equal. It's not equal at A and it's not equal at B. So what we want to do there then is to draw an open circle at A and an open circle at B. Now, if we're going to be greater than A but less than B, we want to be to the right of A. So everything would be to the right of A here if we were just talking about greater than A. Everything less than B would be to the left. So where that overlaps, where we kind of have that shaded region overlapping, this is going to be the value that we're talking about, or the values that we're talking about here. So because this has a but, or the word but or and, we're looking for the overlapping of those two inequalities to get our graph. Now as we graph this, or as we write this in interval notation, x exists within A, this time with a bracket, a parenthesis would be our leftmost value on the number line. B would be the rightmost value on the number line. And so there we have an inequality, a graph, and interval notation. The last example we have before we get into kind of a word problem here is D, where it says x is less than A or x is greater than B. This is important, that word or. So in C, I joined these two because it was a but or an and. I could put these two inequalities together. In D, because it's an or, we're going to keep the inequalities separate. So x is less than A or x is greater than B. So as I come to the graph this time, we can again deduce that A is to the left and B is to the right. We're not equal at A and B, open circles. Less than B would be shading to the left of, less than A would be shading to the left of A. Greater than B would be shading to the right of B. And so because this is an or, there's no overlapping of the two. We're just looking at what satisfies this first condition and what satisfies the other, not both. Where in C, we were looking for both. In interval notation, x exists within. So if I look at that shaded region, the furthest we get to the left is negative infinity. Then we go from negative infinity, it's shaded all the way up to B. So we're going to close this parenthesis at, not B, all the way up to A. So we're going to close this parenthesis at A. Let me rewrite this here. So negative infinity to A and close the parenthesis. But we're also going to continue on the other side of B. So we need a second interval where we start at B and we continue to the right forever. So we would have two intervals here. X exists within negative infinity to A or B to infinity. Now another symbol that you might see, or you will see, that we'll talk about later is what we call a union. The word or can be replaced with a union of two intervals. So you could write this as or you could write this symbol with that looks kind of like a U, meaning union. We'll continue to write that as we progress further in this unit. So these are 4 different scenarios where we can use a graph, an inequality notation, and an interval to represent values in comparison to one another. Now let's take a look at E. It says a word problem here. If the ball had traveled at least one more foot in the air, it would have been a home run. So in this case, we want to somehow write an inequality for this. So there's a variety of different ways that you can write it, but let's let D equal the distance needed for a home run. So if D, or let's say if X was, sorry, let's say here that, let's let B be the distance that the ball traveled. So then if D is the distance needed for a home run, D would be B, sorry, D would be greater than or equal to B plus 1. So what we would need is the ball, how far it went, to go one more foot further, or if it went 2 or 3 or 4 feet further, then it would be a home run. So how we can represent this on a graph? Let's let B be on that graph. But B's not far enough. So let's let this be B plus 1 on the graph. B plus 1 would be a closed circle here because B plus 1 is far enough for a home run. And then it would be shaded to the right. So then in interval notation, the distance that we needed for a home run, let's let that be D. D exists within the interval where B plus 1 is the furthest we are to the left. And that gets a bracket because that is far enough for a home run. And then to infinity. So if it goes further than B plus 1, and it continues and it continues and it continues, then this would be a home run. So this is how, one way, not the only way, but this is one way that we could represent the distance needed for a home run. It would be the ball, how far the ball traveled, plus 1, greater than or equal to that value. So this is probably some stuff you are familiar with from Algebra 1. Definitely writing inequalities. You did a lot in Algebra 1. Graphing and using interval notation, maybe less of that in Algebra 1, but we are going to see a considerable amount of that here in Algebra 2. We're also going to solve linear inequalities. And so that's the main goal for today, is to be able to solve linear inequalities. Solving linear inequalities is pretty much the same process as solving a linear equation. There's one very slight difference. And that difference comes through this property that we have displayed. So it says given A, B, and C are algebraic expressions, so A, B, and C could be numbers, they could be variables, such that A is less than B. We know A is less than B. A times C is going to be less than B times C when it's positive. So if I take two values and I multiply them by a positive number, the inequality is going to remain the same. However, if I take two values, A and B, and multiply them by a negative number, C, this case number 2, the inequality switches. So anytime we multiply an inequality, both sides of an inequality by a negative number, that inequality sign is going to have to change. Let me show you that with some numbers. So we can all agree here that negative 3 is less than negative 2. Negative 3 is less than negative 2. But if I multiply those together or multiply those by negative 1, let's multiply them by negative 1. So negative 3 would become positive 3. 2 would become positive 2. If I don't change my inequality, this is not true. It would say 3 is less than 2, but that's not the case. 3 is actually greater than 2. So therefore, I need to switch my inequality anytime I multiply both sides by a negative. This is going to be the one difference that we see in solving linear inequalities. So now let's take a look how that actually works in equations. Let's look at problem number 2. It says to Solve the inequality and list the solution as an inequality in interval notation and graphically when possible. So we're going to list our answers the same way we did on the last page. Now, solving this equation is going to be the same as solving a linear equation with one difference. We have to make sure we take care of that inequality here in the process. So if you think maybe in this case it's simplified. So I want to move the 1/2 over to the right. Now you could get rid of the denominator. You could multiply everything by 6. That would be okay. I'm going to leave that for right now to show you an example of how we can work with the fractions. So if I want to move the 1/2 to the right side, what I can do here is I can subtract 1/2 from both sides. So I'd subtract 1/2 from the left. I would subtract 1/2 from the right. I am subtracting, not multiplying. There's a difference there. So when I subtract 1/2 from the left, negative 2/3 x stays the same. My inequality stays the same because I am not multiplying, I'm subtracting. Now you can do the subtraction in the calculator if you don't want to worry about finding a common denominator. So 5/6 minus 1/2. The calculator is going to give me a decimal, but I can hit the math key and change that into a fraction. And it's going to be 1/3. So now I have simplified this equation a little bit. Negative 2/3 times x is less than or equal to 1/3. I need to get rid of this coefficient. So you can do one of two things. You can divide by negative 2/3, or you can multiply by the reciprocal, negative 3/2. So I'll go ahead and multiply by the reciprocal. So as I multiply by the reciprocal, the negative 2/3 and the negative 3/2 will cancel each other out, and I'm left with just x. Now, one thing I do need to make sure of here is that in this instance, I am multiplying both sides by a negative number. So I need to switch my inequality. So it's going to be greater than or equal to. Now as I multiply 1/3 by negative 3/2, I would come up with negative 1/2. And so this would be my solution. X is greater than or equal to negative 1/2. So I can graph this. Actually, let's go ahead and check this solution first. Let's check. So I can check this using the graphing calculator by substituting in values for x. So let's see if I get negative 2/3. Oh, sorry, let me clear this out. If I take negative 2/3 times negative 1/2 plus 1/2, and I put that in a fraction, it's 11/6. Oh, sorry, I typed this incorrectly. There we go. Let's change this to a negative 1/2. Now it's correct. It is going to give me 5/6, which is less than or equal to 5/6. Now I could also use a number that's greater than negative 1/2. So let's use 0. So I do negative 2/3 times 0 plus 1/2. And that would be 1/2. 1/2 is less than or equal to 5/6, so this would still work. So we do have a good solution here. So x is greater than or equal to negative 1/2. If I want to graph this, I'm going to graph it first. So I'm going to put negative 1/2 on the number line. It is equal at negative 1/2, so I'm going to close my circle there. And then I'm going to shade it to the right because it's greater than. So everything's going to be shaded to the right there. If I want to write an interval, x exists within. Negative 1/2 is the furthest left that I write here. And then it goes on to infinity. I do have a bracket around negative 1/2 because it is equal at that location. And then a parenthesis around infinity because we can never get there. So the solving process is the same as linear equations. How we represent our answer is slightly different. And making sure we account for multiplying by a negative here and changing our inequality is something that is new. Let's take a look at another example. Example B here. If I were to multiply this, you might say you would want to simplify by distributing, and that would be correct. So I'm going to go ahead and distribute this negative to both terms here inside the parentheses. And then I'm also going to distribute that 2 to both terms. So 2x minus 8 minus 5x. Now I can simplify this. So I'd have a negative 3x. I'd have 7 minus 5. 7 minus 5 is 2, positive 2. I would combine my 2x and my negative 5x to give me negative 3x minus 8. Now it's simplified, so I want to get my variables to the same side. So I'm going to add 3x to both sides, subtract 2 from both sides. When I do so, I get 0 is greater than or equal to negative 10. Now, this doesn't give me a single value for x, but look at that statement. That statement is true. 0 is greater than or equal to negative 10. What this tells me, when I come down to a statement, in the previous target, we found some statements that were false. It might say 0 is equal to negative 8, which is not true, and so we said there's no solution. If you come out to a statement that is true, always true, 0 is greater than or equal to negative 10, which is true, that means our solutions are all real numbers. So you can write out all real numbers, but also this is a symbol for all real numbers. So if you write the letter R with double bar, that means all real numbers. So x in this case is all real numbers. If I want to graph that, I can graph any number on the number line. Let's say 0. I'm going to shade it. I'm going to close a closed circle on 0, and I'm going to shade to the left, and I'm going to shade to the right, because it does cover everything to the left and to the right. So this interval would be going to the left forever, so negative infinity, going to the right forever to positive infinity. So if you do solve and you get a statement that is true, always true, your answer is going to be all real numbers. The last one for this problem, 2C. Same concept. So first, you may say, simplify by distributing. So 3x plus 12 minus 5 is less than 2x minus 6 plus x. Then we would want to simplify in this case. So 3x plus 7 is less than 3x minus 6. Again, we want to get the x's on the same side. We want to get the constants on the same side. When we do so this time, what we come up with is that 0 is less than negative 13. This is actually not true. So when we solve a problem and we come up with a statement that is actually false, then x has no solution. So you can write it out as no solution. If we wanted to graph that on a number line, we would graph that. We could put down 0 with an empty circle, and we would shade in neither direction. We would say x exists within the empty set for notation. So multiple ways here to write this one. Generally, we won't really graph no solution. We won't put it in interval notation. So the solving process for a linear inequality is the exact same as a solving process for a linear equation. The difference that we incorporate is the way that we represent our answer, and making sure that if we multiply by a negative number on both sides of the equation, we switch the sign of the inequality. This is a good place to stop for our notes. Tomorrow in class, we will go over any questions that we may have, potentially take a look at a couple more examples, and then give you some opportunity to practice some of these techniques in your homework. Over the next couple of days, we will continue on the EI.2 notes, and we will finish that, and then that will be the conclusion of this unit. Thank you guys for tuning in.